Good morning, everyone. My name is Garud Iyengar. I am at the Department of Industrial Engineering and Operations Research at Columbia University. About 25 years ago, I graduated from this esteemed university, or what do you call it, Institute of Technology. I was an electrical engineering student here, went to do electrical engineering at Stanford. Somewhere along the way, I sort of meandered into operations research. So my take on many of these things tend to be coming from different perspectives. Before I start, I want to just to sort of get an understanding of where the students are and what you have learned before, so that I don't go and do things that make no sense at all. How many of you are undergraduate students? Perfect. How many of you are master's students? Okay. And how many of you are either PhDs or have done PhDs? Okay, so about half masters, half PhDs. Perfect. In terms of in the first module, I'm going to start talking about maximum likelihood estimates and whatnot. So I just want to get a sense of you, how much probability knowledge that you have, just to give myself some knowledge of where I should pitch things. How many of you have seen this word maximum likelihood, or let me start even before, likelihood? Perfect. And how many of you have seen maximum likelihood estimation? All right, very good. How many of you are conversant with the idea of Gaussian mixture models? Okay, so there it came down. All right, binomial models. Very good. So great. I think we can be moving along. How many of you are happy with Python? About half the class. Okay. How many of you have the material that I was sent out to you? Oh God, this thing goes to sleep. The material that was sent out to you has these things called IPython notebooks. Do you know how to use them? Yes? No? No. Okay. So this IPython notebook is actually going to be part of this course. How many of you have laptops right now? Perfect. So before I start the lecture, I am going to show you this website where you should go and download Anaconda. Anaconda, this is the website. Just type www.anaconda.com. You don't have to do it right away. We will take a break and at that point download it. I'll remind you at the end of whenever we take a break. You go to Anaconda, you download their distribution. You can download it for Windows, you can download it for Linux, you can download it for Mac. And within that distribution, IPython notebook or Jupyter notebook, what the case may be, will come. And the reason I want to do this is because one of the things that has happened, so this is what a Jupyter notebook would look like. I can make it a little bit bigger. For some reason my okay, good, keyboard has died. Okay, so this is what that notebook looks like, and what we will do is interactively do these calculations as we go through it. You would be, whatever I'm going to talk about, a bunch of things, this coin toss problem will come in the lecture notes. We'll go through it. And then in this notebook, we will actually do the computations. So we can play around with it. We can do different parameters, see what it's doing. Since you're here for the data analytics lectures, Python I would recommend highly. And the reason that is if you just keep doing searches for anything, the next topic that I'm going to talk about after expectation maximization is support vector machines. Do a search for support vector machines Python. You will get lots of code. People have been very generous with their time. They have uploaded all kinds of codes about machine learning onto the web, which means that anything that you want to do, you can simply download the code and use it. And in some ways, my job as a professor has become extremely easy because I don't have to teach anything. I can just tell people to use search. And in other ways, this job has become harder because now we are not focused on teaching you how to code, because somebody else does the hard job for you and you simply have to copy the code. Plagiarism is actually allowed. But now I have to focus on making sure that you understand that that code is written correctly. Remember, people who are writing this code are people like you. They have written code, they think it works, most of the time it works, and they upload it and hope that lots of people will use it. They will get credit for it. In some cases, they put it on GitHub. How many of you know what GitHub is? Perfect. So a lot of you know that. Great. So people put it up on GitHub. That way they get, in fact, those of you who want to make a career for yourself in data analysis, data science, you should get a GitHub account and start posting your codes. Nowadays, instead of looking at your CV and resume, people search for your GitHub account and see what you have posted. It's almost like saying you need to be generous with your time as well. Okay, to go back, this is where Anaconda, the Python is available. Within that package, you will get notebooks. So if there is a little bit extra time needed, I will ask Raghu if there is somebody that they could help you download this, because it will be very useful and nice to have that thing running so that you can also interact with the notebook as we are doing things, rather than it being a completely offline exercise. Also, the assignment that will come with this module, you will have to do it within this notebook. So you should really think of that as part of this course. All right, so let's start. Where did my, there we go, view. Full screen mode. All right. So the first topic that we're going to talk about is something called the expectation maximization algorithm. This is an algorithm for doing maximum likelihood estimation in a particular context, which is called a missing data context. In order to set that up, we will go and motivate the problem. I want to also try to step up to where we are, and then we will go back and forth. The first, we will stop at around 10:45 for a break. Till that point, I'm just going to be using the lectures. I'm hoping that in the break we could get this IPython notebook going, and so we can start doing something else around that. Okay. Most of the slides that you're going to be seeing is identical to the notes that you have, but some of them might not be, so don't be surprised as they get updated. So to set the context, what we're trying to do is to solve an inference problem. What do I mean by an inference problem? There are some observations that I'm noticing. Capital X, the boldface X will stand for capital N different samples of this quantity X. In the trivial example that we'll be looking at, these could be the results of coin tosses. So I've taken a coin. The first concrete example that I'm going to talk about is that I have an experiment where I have two different coins. One of them has one probability of heads and tails. The other coin has a different probability of heads and tails. In every experiment, what I do is I pick a coin at random, don't tell you which one it is, toss it a few times, and then tell you the number of heads that came and the number of tails that came. Well, you know the number of tails because I'll tell you exactly. So let's say for concreteness, I pick a coin, toss it 10 times, and tell you the number of heads. That's X1. I'll repeat the experiment again. Next time again, pick randomly a coin, toss it 10 times, tell you how many heads there are. That's X2, and so on. Okay? Now, what I tell you is that you have to figure out what is the probability that a particular coin comes up heads or tails. Okay, I have two coins. You have to guess, you have to estimate for me what is the probability that each coin gives you a heads. And of course, we know 1 minus that is the probability that it gives me a tail. So generally speaking, what we have is we have a model. And the model would be, given some parameter theta, in this particular case, the parameter theta would be the probability that a coin turns out to be heads. Given that probability, I should be able to get the conditional distribution of my X. So the first thing that this model does is that you give me the theta value. I will tell you what the distribution of these outcomes X are going to be. Let's take our concrete case. If I tell you that the probability of a coin turning out to be heads is a half, then what is the distribution of X given theta? What kind of a distribution does it have? If I give you that X is M equal to 10 coin tosses. Sorry? Binomial. Perfect. So binomial with parameter, 1/2. Good. So if I tell you that theta is 1/2, you will tell me that each of these coin tosses are going to be probability binomial distribution with parameter 1/2. Right? So more generally, theta is a number between 0 and 1. If I tell you what theta is, then it's going to be binomial with parameter theta. Now, my problem was, and which is what I want to build up to in a moment, I don't tell you which coin came out. So I have two coins. I pick randomly one of those coins, and we'll go back and see how to fix this. And then I tell you, okay, I'm going to toss with this coin, and you will see whatever it is. Now we are in a situation that P1 is the probability that a head comes in the first coin, P2 is the probability that a head comes in the second coin, but I don't tell you which coin I picked. So now what is the distribution of X given P1 and P2? So let me repeat the story, which is something that I'll describe this a little bit more. So I want to build up to this story. I want you to think about two different experiments. I need to figure out some way that this thing doesn't go to sleep. Give me one moment. So if you drink coffee, you don't go to sleep. That's that little app that will run. Okay. All right. So we will build up to this experiment in a moment. So I want you to think about two different conditions. In one condition, I take a coin out and I tell you what coin it is. Is it coin 1 or coin 2? After that, you get to see X1. So now, if I tell you which coin it is, what is the distribution of X given the parameter value? If I tell you that the coin picked was coin 1, then the distribution of X will be binomial P1. If I tell you that the coin that I picked was coin 2, then X will be distributed binomial P2. Now suppose I don't tell you which coin it was, but I tell you with probability 1/2 I will pick coin 1, with probability 1/2 I will pick coin 2. What will be the distribution of X now? So let's go through the process. The way to construct these distributions is let's go through the process that we constructed it, right? We'll pick a coin at random with probability 1/2. Coin 1, coin 2. Then given that coin, I'm going to generate X binomially. So if I had picked coin 1, the distribution would have been binomial P1. If I had picked coin 2, then the distribution would have been binomial P2. I don't know which one I picked, but I know with probability 1/2 I picked coin 1, with probability 1/2 I picked coin 2, and therefore the distribution is 1/2 times the binomial P1 plus 1/2 times binomial P2. This is a mixture model now. It's a mixture of two distributions. It's a mixture of one distribution being binomial P1, another distribution being binomial P2. Going back here, I have this thing is still going to sleep. I think this story is I have to do something to this. Okay. All right, hopefully I will keep talking and with the slide so that this thing doesn't go to sleep. I just have to talk faster. Okay. Yeah, well, we'll do it later. Maybe there is figure out where to do the sleep time. System preferences. No, I don't want a software update. My keyboard is not working right now, but we'll worry about it later. Okay, I will figure it out later when I have a break. Okay, so going back to this story, I have some parameter theta. In your mind, keep this parameter to be the binomial parameter P1. I have some prior distribution on this parameter. So in our case, the prior distribution was 1/2 P1, 1/2 P2. Or I could have a flat prior over this set. I don't know which parameter is going to come out, and I want to know what the distributions are. Then the inference problem are two kinds of things. One is I want to maximize the maximum likelihood estimator theta star would be out of this set theta, capital theta or big theta, pick little theta such that it maximizes the likelihood of the data given the parameter, right? I put a log here in front. So if the likelihood is just this part, probability of x given theta. I put a log. Log is a monotone function, and therefore whether I maximize probability p or I maximize log of p, it's going to be the same. But very often these data points are IID, meaning independent, identically distributed, and therefore the probability of big X, capital X, which is the joint probability of x1 through xn, will become a product. Because they are IID, the probability of the entire vector, capital X or boldface X, is going to be a product of all of these. When I take a log, it becomes a sum. We love sums compared to products, and therefore maximizing the log likelihood turns out to be a better idea. So we're going to work with that in a moment. Another possibility to do is to look at the posterior distribution. Prior distribution was p theta. I observe x, and now having observed x, my belief about theta changes. The story here is that I could have, again going back to this coin example, I have a whole family of coins. I pick one of them and keep showing you what's going to happen. Before I started the experiment, any possible value of p was valid. It could have been any possible value. But now if I start showing you different values of x1, x2, x3, xn, now your belief about what coin I picked starts to become better and better. As you take xn to infinity, n to infinity, you should know exactly which coin I picked, or you should come very close to it. All right, I think I have to take a break and fix this problem. For some reason, it's not detecting my keyboard. Give me one moment to figure this out. Is there somebody with a computing capability here, if possible? And so I don't slow down the story. Okay, display, screensaver.
I think you can go to energy settings and
that should hopefully solve my problem.
not extra keyboard also.
No, it's fine. Let me see whether this will solve my problem, and hopefully life would be all good again. Okay, so we can get the posterior distribution. For most of the expectation maximization module, we will not be worrying about this posterior distribution. We'll all be looking at the maximum likelihood estimate. Right? We won't worry about how to get the posterior distribution, but this is starting to become interesting. Tomorrow, depending upon where I get to EM today, I'll get to something called SVMs, where this posterior distributions will start to be applied. Now, this story is great if I observe everything. So going back to this coin example, if I tell you which coin I picked and I tell you the value of x, computing the probability of heads for that coin is very easy. What will it be approximately? Suppose I tell you that I pick a coin, I toss it, and out of 10 times that I tossed the coin, 8 of them came out to be heads. So what is your estimate of the probability of that coin? So how much? 0.8. Now, just to get the intuition right a little bit, are you really confident it's 0.8? What is the standard deviation around it? Can you get that from just one observation? NPQ. Yes. But you don't know P, you don't know Q. P because you're estimating the P and the Q.
P 0.8, Q 0.8.
And what is N?
10.
10. Perfect. Very good. It's square root of that because that's the variance. Square root of that is the standard deviation. So N was 10. P, your estimated value was 0.8. Q, which is 1 minus P, which estimated value was 0.2. N times P times Q square root will give you the standard deviation. So with one observation, you don't know things very well. You get a second observation and a third observation and so on. You start to get things better. But now if the coin is not available to you, now you need to figure out what to do. So I tell you that there are 2 different values, P and Q. Same experiment. I gave you 10 heads, but now there were 8 of them was heads. Now it could have been one of 2 different coins. Would you be able to differentiate those coins with just one observation? No. So you need more observations. So you need to figure out how to get, and suppose I give you 2 observations. One time you got 8 heads, the next time you got 7 heads. Would you be able to differentiate the coins? But I won't tell you which coin I picked. Will you be able to tell me the P of the 2 different coins? I give you 10 of these experiments. Would you still be able to tell me? You should be able to tell me something. So this whole expectation maximization module in a way is about that. How do I figure out, given experiments that could be 2 or 3 different causes, which cause goes with which one of the experiments is not known to you, and I want to be able to figure out by looking at the experiments not only what caused it and what was the probability or what was the parameter associated with that cause. The story there is that some observations were missing. Missing meaning I didn't tell you the coin. Or another word for the same thing is latent. Latent is another word which says hidden. So we pretend as if that this observation exists, but somebody just hid it, didn't tell me. And I want to be able to figure out what to do with it. Okay. So the complete data set Z is XY. X is the observations that I am seeing, Y is the observation that I should have seen, and life would have been great had I seen it, but it's unobserved, it's latent. The joint distribution of the data now is P of X and Y given theta. And what I want to be able to do, here's the coin toss example. 2 coins A and B, probability of heads theta I in AB, so theta A and theta B are 2 parameters. The data generation process, pick a coin Y in AB at random, toss the coin M times and record the sum X, which is binomially distributed with M, which is because I tossed it M times theta Y. The complete data set that you end up getting is X1, Y1. X1 is the result of this binomial. Y1 is which coin did I pick, X2, Y2 and so on. Now this is the maximum likelihood estimate with the complete data. So you want to take the argmax of log of the product of, you take the product for I where yi is equal to y. So if I'm trying to estimate what happens to coin A, so theta star A, I only focus on those coin tosses where y was equal to A. So theta star A is argmax of theta log the product yi is equal to A, theta to the power A, or theta to the power xi, 1 minus theta to the power m minus xi. I is taken, many of these experiments have happened. I estimate what this term is going to be, and if you take a log of that, it becomes this quantity, and the estimate turns out to be very easy. It's the sum over all i's where yi is equal to y of xi. This is just counting the number of heads. This is number of experiments that had yi equal to y divided by m, which is the number of coin tosses that happen. So this looks a little bit more complicated, but only thing that I'm doing is each coin toss is independent. Already you guys told me that xi over m would have been the estimate for one coin toss. For one coin toss, x1 over m was the estimate of that particular heads probability. Now I have had many different experiments. How many different experiments? The number of times yi was equal to A, let's say. So I take the sum of xi's where yi is equal to A divided by the number of times yi was equal to A and m. That gives me theta star y. For those of you who are finding this a little bit rusty, the notes are there, you can look it over again. Right now the only thing I wanted to focus on is that if I tell you the coin, computing this number is trivial. Just an arithmetic. Okay. All right. Now suppose yi's are unobserved. We don't know which coin was picked. Yi are unobserved or latent. Now what happens? Now you have 2 possibilities for each experiment. So I goes from 1 through n. These are the different experiments that have happened. For every coin toss, I don't know which coin I picked. There is some probability that yi was equal to y, meaning either A or B. Theta y to the power xi plus 1 minus theta y to the power m minus xi. And now I want to maximize this quantity. The difficulty here is this is a hard optimization problem because the summation over y lies inside the logarithm. If this was outside the logarithm, which is what happened over here, when I take the log, it becomes a summation outside the logarithm. I know the answer. When it's here, I have a problem because now I have two parameters that I'm supposed to optimize, theta A and theta B. And they're both sitting inside the optimization problem somehow, and I need to figure out what to do. Okay? And this is precisely the story that expectation maximization algorithm tries to attack. People generally with me so far?
Yes.
Good. So if you have a question, stop me. I tend to go fast. So if you have a question, please stop me. I'll be happy to go over whatever is going on. Now let's say, how do I figure out what to do with this quantity? Here's a heuristic. You make some initial guess for theta A and theta B. Let's say that I take theta A to be 0.25, theta B to be 0.75. I have two different coins. I make some initial guess. Based on those initial guess, I can decide for each of those experiments xi whether it came from coin 1 or coin 2. Was it coin A or coin B? I can make a guess. So once I make the guess, I now complete the data. For every coin toss, I also put my guess of which coin it came from. Once I have that, I know to compute a new value of theta A and theta B, and I can reiterate this. I can keep on going. And I will show you once we are done with the break and you have the notebook set up, I can show you how exactly this is going to work. The question now is there a mathematical justification for this procedure? Can I make sure that these procedures actually make sense? It sort of has a feel that it should make sense. I'm going to guess something. I'm going to check whether the guess works. If it doesn't work very well, I'm going to re-optimize and keep going. And I want to be able to understand what is the justification for this. There are two reasons for it. First, to of course make sure that I understand what is going on. But there's also another piece, is that once I understand this simple coin toss problem, maybe I can use the same idea elsewhere. Wherever there is missing data, maybe I can start thinking about how do I fill in that missing data. That's the story that I want to go to. Here I'm just saying y hat I is the maximum. Can I have a different assignment for y? Another thing that you could think about, which is what we'll come to see, for those of you who have seen some amount of data mining or data analysis before, this is like classification, right? Because what's happened is that there are two possibilities. Either it was coin A or coin B. I showed you the number of coin tosses, and what I'm basically doing is classifying that coin toss into either A or B. That's what's going on over here. But many of you who have done some classification also know that there is a soft classification also possible. Instead of doing something called a hard classification which says A or B, I can do something soft. I can say it's 90% likely A, 10% B, or vice versa. That seems a little bit better because at least I'm not making a full commitment that this came from this coin or that coin. Because consider the possibility that the probabilities were not 90-10 but 55-45. Then if I arbitrarily just took coin A versus coin B, I'm making a huge error. Maybe instead of doing this, I should be doing this soft classification. Does that make sense? Again, at this level, it of course makes sense. I can make a lot of other things also make sense. But we need some model to be able to argue that all of these things that in words make sense, what can I do to justify it? Okay. Let me give you another example. This is actually something that happens a lot in classification. It happens a lot in a lot of different data analysis, and towards the end of this module, we'll see an example where this happens a lot. So here, the model that I'm proposing is that the observations are coming from m different classes. This is a classic classification problem. A person walks in, they are in one of m different classes, and when you look at the observation associated with this person, it's normally distributed with mean mu j and sigma j. Depending upon which class the customer comes from, probability y equals j is alpha j. J takes values 1 through m. The probability that belongs to a particular class is alpha 1, alpha 2, alpha m. When they arrive, then given their class, the observation X is normally distributed with mean mu j and standard deviation sigma j. The parameter that describes this model is alpha, the probability of the different classes, mu's, the mean of x's for each of the classes, and sigma j, which is the standard deviation for each of the classes. And right now we are assuming that x here is one dimensional. If it's not one dimensional, then mu will become a vector, and this matrix, this sigma, will become the variance covariance matrix. For now, just to keep everything simple, let's assume that these are just one dimensional distribution. Again, the story is the same. What I want to do is I've got a whole bunch of x's that I observe, but I don't observe the y's. So the y's, which are the classes, are typically not observed. To give you a very concrete example, somebody shows up at your store and you are trying to sell them a laptop. Depending upon, you have to quickly guess whether they are a high net worth customer or a low net worth customer, because if you guess if somebody is a low net worth customer and you show them a laptop which is very high cost, they're just going to walk out. You will lose the sale. If somebody was a high net worth customer and you showed them a low cost laptop, you lost on an opportunity to get high revenue. So you need to be able to figure it out. Well, we kind of look at the person and say, well, I have some idea based on the clothes they're wearing, based on the watch that they're wearing, and so on. But we don't know exactly what's going to happen. So what we want to be able to say is the x is the observation, whatever observation that we have seen. We know how that is distributed given the class, but we want to be able to infer the class from the observations. If, on the other hand, the data was complete, meaning I knew xi and I also know yi, I also know the class they came from. Suppose x and y were both observable, then how do I estimate the alpha, the mu, and the sigma? It's trivial. I look at the number of people that I saw that belong to class j. So Sj is all values of I where yi is equal to j, and nj is this summation, is just the number of elements in this set. So look at all the people who had class j, call that nj, divide by n, which is the total number of people that you saw. This is the estimate for each of the classes. How do I get the estimate for mu j? I focus on only those values of x that belongs to the set Sj and take its mean value. It just sum all the x's, divide by nj, the number of elements of that set. How do I get to here? Well, again, I do the same thing. Mu hat j is already known. I look at only the data points that belong to that particular class. I square it, and then I divide by nj. Well, it could be nj or nj minus 1, depending upon whether you want an unbiased estimate or not. So this is actually the maximum likelihood estimate, but this is biased. So for this particular module, we are going to assume that this is nj because we are focusing on maximum likelihood estimates. We are not looking at unbiased estimates. Okay? So that's sigma hat j squared, and life is honky-dory. So again, if I know the labels, I know the class labels, I can estimate the parameters very easily. Just like with the coin example, if I knew which coin I picked, I can estimate the parameter very easily. But what if now I don't know the y's? Suppose y's are not observable or latent. Again, if you think about it, this is what is going to happen. The probability of seeing the data is what? It's a sum of I going from 1. This is not, just correct this is not little n but capital N. This is the number of data points that I have. They are IID. What is the probability of seeing a particular data point xi? Alpha j is the probability it gave from class j. If it came from class j, the probability of seeing the xi is just a normal distribution, normal density with mean mu j and standard deviation sigma j. I sum it over because I don't know which class they came from, and that summation, this log is simply taking the log of the distributions, and this summation outside is coming from the fact that they have a capital N IID experiments. Now life looks a little bit more complicated because everything is mixed up here. The different classes are mixed up. I won't be able to figure out which of these xi's to do it. Okay, now let's see what can we try to do in this particular case. Remember, what did we do with the coin? We had a heuristic which says for every coin, guess. So how would we guess here? What would we do? What would be the experiment, or what would be the idea that one could run here? And then we'll go back and try to figure out how to fix this story. We'll make more concrete ideas, but right now I just want to get a feel from you as to what you would do in this case. For those of you who already know this Gaussian mixture model, don't answer, because I want people who don't know it to sort of get the idea. So let's take the case that we did with the coins. What was our guess there? First, what did we start from?
Initially we estimated the values of M and F.
Sorry?
Initial probabilities.
We just guessed an initial probability. Perfect. And then what did we do about, what was the second step that we did? For every coin toss, we classified it into either coin 1 or coin 2. So here, what will be the analogous statement that one would do? How would we go about this story here in this particular case? What would be the initial guess I would make? Life is a little bit more complicated here, and that comes from, so let's start it and then I'll tell you why it's a little bit more complicated. So let's say that we want to analogously do the thing that came from the coin toss. So what would be the initial guess I would make?
Out of M classes, it belongs to one particular class.
Yes, but before I do that, what do I need to? I need to start with an initial guess for which parameters? Sorry? Alpha. No. Not alpha. Remember, what did we guess? We did not guess which coin it was. We guessed what the probability of the coins were. Mu and sigma. Perfect. So we're going to make guesses for each mu and sigma for 1 through m. We're just going to guess. Randomly choose the value of mu1, sigma 1, mu2, sigma 2, mu3, sigma 3, and so on. So once I have these mu's, now I can look at the probability that a given value of xi came from one of these classes. And I can do a hard classification. I could say that the class that gives me the highest probability, let's assume that it came from that class. Complete the data, and now I can keep on doing. This is exactly analogous to what was happening before. Or I could also do this estimate where I could say that the probability that it came from that particular class is just the probability f g xi given that quantity. There's one problem though. The problem is, in the coin toss example, I had told you that it's probability a half that it's each of the coins. This time I'm telling you that the probabilities need not be equal. So now we have a problem, because even though the probability coming from a particular class is very high, there might be another class which has a very high probability. Most of the people, 99% of the people come from one class, 1% of the people come from another class. So now, even though this 1% class gives me a higher probability compared to this 99% class, I need to be able to somehow reweight it. I need to be able to say, wait a minute, even though this probability is high, I know this class doesn't come very often, so maybe the 99% one wins out. But I can't just arbitrarily say 99%, because then I'm not taking any information about the mu's. So I need to be able to somehow balance this. The point that I'm trying to make is that we need to be able to develop some methodologically firm idea of how to do this, and I'll show you how to do this. So in the coin toss, life was easy. I could classify because half probability, and I could redo the things. Here I will try to do the same thing, but it's complicated by the fact that there is that alpha sitting, and I need to figure out what to do with that. So this is basically the heuristic. Assign data points xi to classes, y hat I is 1 through m, estimate mu sigma using the complete data set z. How do I create y hat? We just guessed one, that I guess mu's and sigmas, and from that I can figure out classify to y hat, and then do something of the sort. And however, when we looked at this, creating this y hat, we said that I can focus on just this part and create the y hat, but I don't know how to incorporate this alpha. That's a bit of a problem. Or I can focus on alpha, then I don't know how to incorporate this guy. So I've got a problem where I can't incorporate both of them, and I will try to figure out what to do. And then of course, at the end of the day, these are all baby examples. What I'm trying to get at is, how do I generalize this to latent variable estimation? Okay? All right. This story is going to be a little bit complicated. So this slide is the heart of EM. So we will get to this. I'll slowly motivate what's going on here. So the first thing that we're going to start off is something called Jensen's inequality. How many of you have seen Jensen's inequality? Very few. Okay, so let me motivate that. So let's say that a function f is concave. How many of you know what a concave function is? Most of you. Okay, so I'm hoping that this is visible. Here's a function f. I'm going to say that the function f is concave, and for my purposes, if and only if, that's what this double thing stands for, its second derivative does what? For those of you who know concavity, second derivative, Hessian matrix is what? For a concave function, the Hessian matrix has what property? Negative, semi-definite. I let the semi part go. So if I go down here for a one-dimensional function, what does it tell me about the second derivative? Less than equal to 0. Right? Okay. It also has a property that if I take any 2 points, x1, x2, and I take a combination, let's say this is the point x, where x is written as some theta of x1 plus 1 minus theta of x2. What happens to the function value at the point f of x? It's greater than equal to theta times f of x1 plus 1 minus theta times f of x2. That's the definition of concavity. Here is the so the straight line, which is this thing, and this is the function value. The straight line lies below the function value. Everybody good? All right. Now I'm going to write this slightly differently to get to Jensen's inequality. All right. I'm going to pretend that I have a probability mass function which has theta 1 minus theta. Okay, so it's a probability mass function. With probability theta, it picks up the point x1. With probability 1 minus theta, it picks up the point x2. So it's a 2-point probability distribution. This one probability theta, that one probability 1 minus theta. All right. So what is the expected value of f of this random variable x? So suppose the random variable x has this distribution. So what is the expected value of the function of the random variable x? This part, right? So that is theta f of x1 plus 1 minus theta f of x2. Everybody happy? Okay. What is the function of the expected value of x? What is the expected value of x according to that distribution? Out of these quantities that's written over here, it's theta times x1 plus 1 minus theta times x2. Right? That's the expected value of this random variable x, which is exactly equal to little x without the subscript. So this quantity is just f of x. Right? So if I now look at this idea, what does it say? It says that the function of the expected value of the random variable x, where is my eraser? It's over there somewhere. Is greater than equal to the expected value of f of x. Exactly this statement, I can write it as that statement. Everybody good? Now if you don't really have, now nothing in here I used any property other than of the fact that it has 2-point distribution. Anytime you have a discrete distribution, you can always generate it by 2 by 2 by 2 by 2, and you can show that this is true. If you have a continuous distribution, break it up into discrete distributions with, as long as you have a continuous density, you can break it up into small parts. prove this statement, take the limit, everything works. That's exactly what that statement up there is, written in the other way. So the expected value of f of the random variable x is less than equal to the function of evaluated the expected value. One thing to keep in mind, this is actually something that's worth keeping in mind. When you have a function which is concave, removing randomness is good for you. So I have two possibilities. Either I have a random variable x, or I have the choice of choosing its mean value. I take the random variable x, or I choose its mean value. If you have a concave function, you love to take the mean value. You don't like the random variable because of the variability reduces the point, reduces the revenue that you want to get. Okay. For convex function, the entire story is just the opposite. You love variability. Maybe you might luck out and get low costs, and so you take the variable return. You don't take the mean value. Perfect. Now everybody. Now we're going to use this idea in constructing this expectation maximization story. Remember what we were doing before? We were trying to predict my unknown y. We used this classification idea. We could say that y is one of these classes, y is one of these coins, and I also told you at that point that perhaps maybe you don't want to do hard classification. What you want to be able to do is to say with some probability y is equal to some quantity. So let's assume that we predict y according to some distribution q. Right? We look at my x. Based on that x, I'm going to predict what my y is, and for the moment assume that the y is predicted according to this distribution q. Okay? Keep that in mind. All right. So what is the probability of x given theta? It is the integral over all possible values of y, the joint distribution of p x y given theta dy. Just this, I'm just using the probability distribution ideas. I've been given the joint distribution p x y given theta. If I integrate over y, the y disappears and I get p of x given theta. General properties of joint distributions. If I want to get the marginal distribution in x, all I have to do is integrate over y. My problem is this integral is like the summation. I don't like integrals inside. I want that integral to be outside. And so somehow I'm going to try to use this property to drag that integral outside. Okay. What do I have to do to drag that integral outside? Right now that thing looks like this. F, which is log, and what kind of a function is log? Concave, convex? Concave. It actually looks kind of like that. It's a bit more extreme. The log function looks like, here's 1, it goes to minus infinity and does that. So that's a log function, it's concave. So I'm setting myself up. I've got the log function here, which is my concave function. I've got some kind of an integral sitting here, which is kind of like this, because when you compute the expectation of some random variable, you take the integral with respect to its density. I've got a problem that I don't have a density. So I'll fix it by just multiplying and dividing by q. So I divide by q, I multiply by q, nothing happened. But now, whatever this object is, this integral is the expectation of this object with respect to q. That's what I've written over here. It's a log, which is the same as before. The expectation with respect to q, that takes care of this integral, qy dy, of p of x given y given p of x y given theta divided by qy. Y is a random variable. Sorry? Good. So y is a random variable. Its density is qy. So if you write out the expression for this expected value, it's nothing but this. P of x y given theta divided by qy times its density little qy dy. Now I am ready to apply my Jensen's inequality. I have this thing already sitting here. I'm going to drag that expectation outside and claim that inequality holds. So now I'm going to write this story in this way. Expected value of q log p x y given theta divided by qy. I'm going to call this a new function. This new function has two things that I have to guess. I have to guess q, because remember, keep this classification idea in mind. What I'm trying to do is classify from x to y according to q, and then I have to estimate theta, which is the parameter that I'm trying to get at. Okay? That's what has happened so far. So here's what I'm going to do. I'm going to approximate the maximization of this with respect to theta, Lx theta, by maximization with respect to q and theta, two parameter, of this other quantity script L given q and theta. And I'll solve the problem using coordinate ascent. So for those of you who have seen some optimization before, whenever you have a bad optimization to do, which is in two variables, and you don't know how to jointly optimize them, climb in one of them. So it's coordinate ascent. You go in one coordinate, then you go in the other coordinate, and keep going. That's what is happening over here. You have some value of theta k. You maximize this script L q theta k with respect to q. You get qk plus 1. Plug that qk plus 1 over here, maximize with respect to theta. You'll get theta k plus 2. Plug that over here, qk plus 2, and keep going. You'll keep going and until you estimate something that's going to happen. All right? Okay. So so far what has happened is I took some quantity that I didn't know what to do with, and I converted into some other quantity that looks kind of almost as bad, maybe worse, because now I have two parameters instead of one. But what I have managed to do is to take this expectation outside, and that's going to be helpful to us in a moment. Before we get there, I want to show you, we'll get there in a moment. Let me show you the picture of what's happening, and then I'll come back to all of this drama. So here's what is happening. This red line is the log of p of x given theta, and knowingly I have drawn this function in some wobbly fashion, meaning that this function is not necessarily concave, and therefore if I optimize over this function, I will potentially get some local maxima. Right? It could get stuck, like this guy over here is a local maxima, maybe that guy over there is a local maxima. That's the global maximum that I want to go to, but I could potentially get stuck. Instead, what I have done is that at any given point, I'm going to approximate it by this lower bound, which will turn out to be concave, which is this LQ theta. And this has been taken by a book from Bishop. It's figure 914 from pattern matching by Bishop. So if you're looking for a good book on EM, Bishop is a good book. So you find out what theta old is, construct a new approximation, which is the green one, that gives you theta new, which is the tangent point. At this point you construct a new, then it'll give you the next one, and keep on going. So that's the idea. And now what we want to show is that in fact this is not a bad story. So let's go back, and it'll bring up some interesting ideas. So again, returning back, I have my log likelihood only in x, and now I have written it as a log likelihood that involves q and theta, and we want to figure out what to do with this object. So let's first try to optimize this over q for a given value of theta k. So theta k is given. I want to maximize this with respect to q, and I want to see what is going to happen. That quantity is just this: maximize the expectation with respect to q of log of pxy given theta divided by qy. This is what I want to maximize with respect to q. Now, what happened over here? I took this expression, and whenever I have a joint distribution, I can write it using this tower property of conditional distributions. I have to look at the conditional distribution of x and y given theta. So I write it as the conditional distribution of x given theta and the conditional distribution of y given x and theta. Right? It's just simple tower property. This object over here doesn't depend on y. So whatever I do with qy, this object is not going to matter to me. I can pull that out of the log. Right? Okay, I pull that out of the log. And what happened in the next step? I just switched things. So qy was in the denominator, p of y given x theta was in the numerator. I switched the order, and there is a reason why I want to switch the order. When I switch the order, the log becomes a negative of the log. So I want to maximize, in that case, the negative of the expectation of the log of qy over py. Instead of maximizing the negative, I'm taking the negative sign outside and minimizing with respect to q, expectation of q log qy over py. This is just algebra so far. The only thing that went in here is to look at the fact that I can take this joint distribution, split it into two parts. One part doesn't depend on y, pulled it out. Another part depends on y, kept it in. This object is an extremely important object. This thing that you end up getting over here is a very important object. Something called the Kullback-Leibler divergence, another name for it, relative entropy. For those of you who came from statistics, you would call it Kullback-Leibler. For those of you who came from electrical engineering, that I called it relative entropy. It has to be connected to entropy. So it's the relative entropy of Q from P. So its KL divergence, PQ, is written as the expectation with respect to P log P over Q. So it's important that the expectation is with respect to P and P sits in the numerator. That is why I flipped the things over here. I wanted expectation with respect to Q, I wanted the Q in the numerator in order to make it into a Kullback-Leibler distance. So now this quantity is nothing but the Kullback-Leibler distance between Q and the probability of y given x and theta, the denominator. So it's P of x log P of x over Q of x, with the understanding that 0 log 0 is 0. This is what I'm going to assume. This object is important. It's Kullback-Leibler divergence is fundamental in information theory and machine learning. It turns out, and the reason it's important is precisely because it shows the error in estimates. It shows how different are two distributions, and if I do IID measurements, it turns out that this difference matters. But it's a bit annoying, unfortunately, which is the fact that it's not a distance. So it's very important to remember that Kullback divergence between P and Q is not the same thing as the Kullback divergence from Q and P. So, and why is that? Because remember, in the definition, it's the expectation with respect to P, P over Q. If you switch the order, it will become this expectation will also change and this will also change. So it turns out that it's not symmetrical, and it's important to remember that. Very often in many analyses we would like to switch the order, but we can't. And it doesn't satisfy triangle inequality, which is also pretty annoying. So it can happen that the distance between x and y is small, y and z is small, or let's say x and y. In triangle inequality you should have that the distance from x to y plus the distance from y to z or z should be larger than the distance from x to z. It doesn't happen for Kullback-Leibler. You can run into trouble with that. Maybe I can use the chalk over there. Okay, so suppose x and y were both observable. Suppose these were both observable. So to keep in your mind, x is coin tosses and y was the coin. Suppose I can observe both of them and I want to estimate what is going to happen. I would have my theta star would have been the argmax, the maximum, over theta of the probability of seeing this data x and y given theta, and put a log there. And this is what I would have done. Now I don't know y. I have no idea what to do with y. So now what all of this mathematics ends up showing you is, let's create an iterative procedure. You guess a value of theta k. This is a guess. Okay. Given this, I know the distribution of y given my observation and theta k. How do I get this? This is nothing but by Bayes' theorem. This is proportional to the prior on y and the probability of x given y and theta. So I can compute this quantity from the model that I have. So once I have this, I want an analogous statement of this. I don't know y. I have no idea what that y is, but I know how the y should be distributed. So instead of trying to maximize this, what do? I take the expectation with respect to p of y given x and the old value theta k of the log of the complete likelihood function p of x y given theta, and I maximize this. That's what expectation maximization is. This is what I want to do. Why do I want to do this? Because this is simple. In the Gaussian mixture model, in the coin toss model, in both cases, I could write this problem very simply. So I want to somehow get to there. Unfortunately, I can't because I don't have y. So what I do is I guess y. Instead of guessing y in a hard manner and saying this is the value of y, I do it softly. What is the probability of that particular y? I take the expectation of this log likelihood function under that p, optimize this to get theta k plus 1. Go back here. This would update this conditional distribution again. Come back here and keep going until you converge. And we will now see in a little bit how to do this step by step for our various examples and motivate various things. So log the q of theta given theta k has a very nice interpretation. You form the complete likelihood function log L xy given theta, which is log of pxy given theta. What this basically means is pretend that you know y and write out that function. Now you treat y as a random variable, treat y as random and take the expectation conditional on the data that you saw and the previous estimate that you have. Theta k plus 1 is nothing but the maximum value of theta, and you keep going. And we are guaranteed to increase at every point, and therefore we are guaranteed to converge. How fast can we converge? Nobody has any idea. EM algorithm even now, even for two Gaussians, only last year people were able to prove that this converges at a particular rate. For anything more, we still don't know what happens. But it works very well in practice. So let's do it for the coin toss example.